start. So the first talk of this session will be by Lin from CMSA. We'll talk about integrability, symmetry, and protected states in QFT.
Thank you very much. And let me thank Professor Yao and Professor Zhang for the wonderful organization and the planning. And I also thank participants for the wonderful discussion and interactions. So today the title of my talk is Symmetry, Integrability, and Protected States in QFT. So the content that I will cover are as follows. First, I will describe that there is a quantum Hall effect in the subsector of four-dimensional non-abelian gauge theory with supersymmetry. And there's also a gravitational dual for the system. Then I will study the non-BPS sector of the same theory in 3+1 dimensions. And I will focus on operators in the non-BPS sector. And I will present that there's integrability in these operators, and the spectrum of operators can be constrained. And then I will also talk about that there is a symmetry algebra arising from the quantum dynamics of the system. And this symmetry algebra acts in the space of operators, and therefore it acts in the space of observables. So this symmetry algebra is not a symmetry of the Hamiltonian, or a symmetry acts on the fields in the system, but rather it's a symmetry acting on the observables. And the spectrum of the operator is protected by the symmetry algebra. And the particular operator that I will be using is the restricted Schur polynomials. So it's a polynomial of fields in the system, labeled by representations of products of symmetric groups. And there is a non-planar large N limit where these operators can be mapped to a system of harmonic oscillators and is integrable. And because the system is a system of harmonic oscillators, so there is an underlying harmonic oscillator algebra. And this oscillator algebra acts on a pair of long rows of the Young diagram, because operators are labeled by Young diagram. And when we look at the Young diagram, we can look at the action of the algebra on a pair of long rows. And this algebra can be reached by Inoue-Wigner group contraction of the U2 algebra of two D-branes on the gravity dual. And then I will also discuss relation between the oscillator algebra and the higher loop dilatation operators. This dilatation operator is a dilatation generator in the conformal field theory. And it is a matrix which acts in the space of operators. And the diagonalization of such matrix will lead to a eigenvalue of the scaling dimensions of operators in the conformal field theory. And because this oscillator algebra will act on these dilatation operators, so the eigenvalue of the scaling dimensions are constrained by the oscillator algebra. And there's evidence that at one loop and two loop order, there's integrability in the system. And here I use the oscillator algebra to analyze high loop dilatation generators. Now let me briefly overview the relation between operators in field theory and their gravitational dual descriptions. So in the context of CFT-ADS duality, the super-Yang-Mills theory on R cross 3 sphere is equivalent or due to a string theory on a curved ADS5 background with a boundary R cross 3 sphere where the non-abelian theory is defined on. And the parameters of the two theories are related by, for example, the string coupling constant is proportional to the gauge coupling constant squared. And because here the gauge coupling constant is a coupling constant of open strings, and this is a coupling constant of closed strings, and Since closed string is a copy of two open string, therefore it is related by a square formula. And here R is the radius of curvature of a ADS space, and LS is the string length. And this number is very large when the coupling is large, and this is the 12 coupling. So in this relation, the scaling dimensions of a gauge invariant operator in the field theory side correspond to the energy of states on the gravity side. Another interesting feature is that when the scaling dimensions of the operators are increased parametrically with respect to n, there are different kinds of degree of freedom on the gravity side. For example, if n is very large, and then if the operator is composed of number of fields which doesn't grow parametrically with n, which, for example, is order 1, and then those operators correspond to fields on the gravity side that are perturbative fluctuations, for example, gravitons. And if the scaling dimension of operator become very large, grow with n, for example, as a square root of n, then these operators can also describe string excitations on the gravity side. And those are very quite heavy states, heavier than ordinary gravitons. And further, if the scaling dimension further grows and grow as n, then they can also describe branes, which is even heavier. And then suppose the scaling dimension grow further to, say, n squared, then one can consider these operators as a composite operators of this kind, but with many number of them in the product. So then those are equivalent to many branes, and therefore they create new geometries which deform the space-time. So now let me discuss the details of the n equal to 4 super Young-Mills theory. It has an action which contains the Young-Mills term and also 6 Higgs-like field, and as well as fermions. One can look at a subsector of the theory whose dynamics is equivalent to a quantum Hall system. Because one can isolate the half-VPS state, which is built from one matrix field. And because of a supersymmetry, the effective dynamics of the subsector is captured by just one matrix. And we keep only the zero mode on the 3-sphere. And because of the conformal coupling to the curvature of the 3-sphere, this field has also a mass term when reduced to only time direction. And then this is a standard harmonic oscillator system. One can reduce this matrix to degree freedom of the diagonal elements and off-diagonal elements by using the UN transformations. And when one can integrate out the off-diagonal degrees of freedom, leaving only the diagonal degrees of freedom, and it's giving a Jacobian. Then the Hamiltonian can be written in this way. After redefinition of the wave function and the Hamiltonian by absorbing factors of the Jacobian, the Hamiltonian become a Hamiltonian of non-interacting fermions. And the degree of freedom is only the diagonal part. And then there's n fermions. Because of this factor, there's an anti-symmetrical property of the wave function. And these wave functions are the wave function of n fermions in a magnetic field. And therefore, it's an integer quantum Hall effect. And these integer quantum Hall effect, the state can be described by a quantum Hall droplets on the 2-plane. And those quantum Hall droplets on the 2-plane can also be mapped to a gravity configuration in the 10-dimensional string theory. Because the underlying theory, n equal to 4 super Young-Mills, is due to string theory in ADS phi cross S phi. And then in this case, the quantum Hall droplet is a droplet on a certain plane, x1, x2 plane. Because there's totally 10 dimensions. There's other 8 dimensions, which include 2 3-spheres, which are symmetry directions. And then a time direction and a y direction. Y is a radial direction, which is a product of the radii of the 2 3-spheres. And on the x1, x2 plane, droplet plane, because y goes to 0, so that means that either of the 2 3-spheres shrink to 0 size. And the 2 3-spheres shrink at different domains in the x1, x2 droplet plane corresponding to the occupied and unoccupied regions for the M fermions. And the x1, x2 plane can be mapped to the phase space of the fermions. And these Harvey pair states can also be labeled by using symmetric group. And this is the Schur polynomial, where the I1 and I sigma 1 are the indices for the matrix Z, and the sigma is the element of the permutation group Sn, where n is the number of fields. And the trace is character of the sigma in the representation R. And this is sum over all the elements. And in the free theory part, this operator has a diagonalized two-point function, where the Fr is the product of weights of the Young diagram R. And R is an irreducible representation of the symmetric group Sm. So the above example is an example when there's one matrix field. One can also consider other more complicated situations where there's a two or more matrix field. And in these cases, there are several labels of the operators. The operator has a dimension very large of order n. And one label is by using restricted Schur polynomial, which uses the product of several symmetric groups. And another label is by using the representation of Brauer algebra. The Brauer algebra is a generalization of the symmetric algebra. It's by adding contractions. And the third label is by using global symmetry basis. When there are a number of fields which are related by global symmetry, and one can use a global symmetry basis. These bases can all be transformed between each other in a linear way. And the spectrum of such operator corresponding to excitations of the d-branes, because they are of order n in the scaling dimension. And these have been recently studied, and it turns out these spectrum can be exactly solved at 1 and 2 loop level. And then and there is also integrability. So these operators mix under the dilatation generator. So one should diagonalize the scaling dimension of the operators in the space of the operators. And it turns out it can be diagonalized by harmonic oscillator states and by double coset ansatz. Because in the operator, there are several matrix fields. One major matrix field is the Z field, which has more numbers than other matrix fields. There's also other matrix field Y or X, but those are smaller in number. So we can call this matrix field as impurity matrix field. So the double coset ansatz is a method to diagonalize the Young diagrams in the space of the impurity matrices. And the harmonic oscillator state finally diagonalizes the space of the Young diagrams of the major Z matrix field. And so the final problem is mapped to a system of harmonic oscillators. And this is field theory side. On the gravity side, these harmonic oscillator dynamics are mapped to open strings stretched between a pair of giant gravitons. So there's a pair of d-branes, and then there's open strings stretching between them. Their excitations are described by these harmonic oscillator states. So for example, in the angle 4 non-abelian Yang-Mills theory, suppose we look at two scalar fields Z and Y. These are adjoint Higgs-like field. And then one can build a restricted Schur polynomial by using permutation algebra Sn and Sm, where n is the number of Z field and m is the number of Y field. And I1 and I sigma 1 are the indices of the matrix field. And this trace is a restricted character of the sigma element. And there's three Young diagrams in the label. Small r and small s are the irreducible representation of Sn and Sm, respectively. And the capital R is an irreducible representation of the symmetric group Sm plus m. P is a projector which projects from the carrier space of R to the carrier space of R comma S. So this is called a restricted Schur polynomial. So these polynomials in the free theory part can have a diagonalized two-point function, and their normalization can be written down by the data of the Young diagram. And these are the product of weights of the Young diagram. And these are the product of Hooke lengths of the Young diagrams. And by using this information, one can build also normalized operator whose two-point function is normalized, also normalized. And then in the field theory side, these operators labeled by 3 Young diagram will mix under the dilatation operator. So their scaling dimension is a matrix, and it has to be diagonalized. When the dilatation generator acting on this operator, it goes to other operators with other Young diagrams. And this is a mixing matrix in the space of Young diagrams. For example, in a one-loop order, one can compute, and the mixing matrix goes as this. And one can have a simplification when the Young diagram has rows with the rows very long and well separated. Then this mixing matrix can be factorized into 2 parts. The first part is M. This M is a mixing matrix in the space of Young diagrams of the impurity matrices. And this delta Ij is the mixing matrix in the space of a Young diagram of the major matrix Z field, which has more numbers in the polynomial. Then one can see that this delta Ij can be written as sum of 3 terms. So these are operations acting on the space of Young diagram. The delta 0, when acting on the Young diagram, is proportional to identity with a certain coefficient. And delta plus, when acting on the Young diagram, will move 1 corner box in a row J and then put it to the row I as a corner box in the row I. Delta minus will move a corner box in the row I to be a corner box in the row J. So therefore, the delta plus delta minus will change the Young diagram by moving 1 corner box. And so the delta will mix Young diagrams that are related by moving at most 1 box. And there's a prefactors. Here, Ri is the length of the row in the ith row. And M plus Ri is the weight of the corner box on the ith row. And it turns out the sum is a discretized version of harmonic oscillator Hamiltonian. And therefore, this can be exactly diagonalized. And in the above examples, so the delta Ij acts on a pair of rows, and each row mapped to a D-brane. So therefore, the delta Ij also acts on a pair of D-branes. So in the above example, we have 2 fields, Z and Y, but one can consider more field, and then one can consider other sectors in the theory. And those all refer to the global symmetry of the theory. Now let me discuss that the above system is described by harmonic oscillator states. There is an underlying oscillator algebra. But this oscillator algebra is related to a symmetry algebra of D-branes on the gravity side. One can see this oscillator algebra can be reached by a U2 algebra by a Wigner-Inunu contraction. Now suppose we start from UP algebra. It always contains a U2 algebra as a subalgebra. And the UP algebra can be represented in the fundamental representation by a P by P matrix E. And it's diagonal corresponding to the weight of the corner box. Now suppose we focus on a pair of long rows labeled by I and J, and we focus on 4 generators. And these 4 generators span SU2 cross U1 algebra. And the representations of these 4 generators can be labeled by Q square and the third component of Q. And one can see that the above calculation of the delta Ij, which is a mixing matrix on the space of the Young diagrams of the Z field, is a linear sum of 2 terms. One is the third component of the SU2 algebra. Another is the U1 generator. That means one can define another set of SO2 generators by transforming the Q1, Q2, Q3. And then these 3 plus the U1 generator span the SO2 cross U1 algebra, which is also the U2 algebra. And then one can see that there is a Inoue-Wigner group contraction of this algebra to a harmonic oscillator algebra, where A dagger and A are the creation and annihilation operator of the harmonic oscillator. And the delta, this is a dilatation generator, which is a mixing matrix, play the role of a generator proportional to the Hamiltonian of the harmonic oscillator. And this is by a group contraction, and the parameter is related to the weights of the corner box. And this limit corresponding to that, considering that the oscillator level is much smaller than the parameter n, where n is the rank of the gauge group. So these 4 generators span a harmonic oscillator algebra. So this algebra is rather robust because it's from the U2 symmetry algebra, where the U2 symmetry algebra on the gravity dual side correspond to the symmetry algebra of 2 d-branes. And so in a strong coupling regime, such symmetry algebra is robust because the gravity dual captures the strong coupling regime of the field theory. One can study the anomalous dimension of these operators. And this is the dilatation generator expanded to the 1-loop order and the 2-loop order, where this G is proportional to G Young mu squared. And dy is the variation with respect to the matrix field Y. So when this operator acting on the field operators, it will bring the mixing matrix of the scaling dimensions at 1-loop order, because this is proportional to G. And at 2-loop order, it has this expression, there's more derivatives. So it turns out at the 2-loop order, the mixing matrix, which is proportional to G squared, can also be factorized under the limit where the row length of the Young diagram are rather long and well separated. So again, this delta is a mixing matrix on the space of the Z, the Young diagram of the Z field. And it turns out this 2-loop dilatation generator can be written as a polynomial of the 1-loop dilatation generator of degree 2. So then one can see that the H-loop dilatation operator in large N limit can be written as the polynomial of 1-loop dilatation operator as a polynomial of degree H. And they can mix Young diagrams by moving at most H boxes. So these operators at 1-loop level can be diagonalized by harmonic oscillator states. And this is the diagonalized operator, where the Qij refers to the oscillator level, and Qij is an integer. And these are the coefficient for the diagonalization. And the eigenvalue of the 1-loop dilatation operator is 4 Qij. So the 1-loop dilatation operator acting on this operator is proportional to G times Qij, Nij, where Nij is the number of open strings stretched between the 2 branes labeled by I and J. And G is the proportion to G Young mu squared. So one can compute the anomalous dimension of such operator after diagonalization. And at 1-loop, it's proportional to lambda, the 't Hooft coupling, and at the 2-loop, it's proportional to 't Hooft coupling squared. But they have a similarity that they have the same similar factor, Qij, Nij, where Qij is the oscillator level and Nij is the number of open strings. So that means this part is the part that is protected by the oscillator algebra. Because of the oscillator algebra, they have this common part. And the rest part is due to different loop orders. So therefore, I refer this part, the common part, as protected by the oscillator algebra. So the one-loop and two-loop dilatation generator can be written as the SU2 Lie algebra generator, as a polynomial of degree 1 and degree 2, respectively. In the large n limit, one can see that the H-loop dilatation generator can be written as a polynomial of this SU2 generator of degree h. So then one can see that this polynomial can also be factorized by another input, is that there exist BPS states which can annihilate this operator. Because the BPS state doesn't have an enormous dimension, so the BPS state has a delta equal to 0. So that means there's a common factor, this factor, which is proportional to the one-loop dilatation operator, which will annihilate the BPS states. So therefore, this is a common factor. So this is proportional to the one-loop dilatation generator in the large n limit. And the eigenvalue of the two-loop, one-loop is proportional to this, and higher loop, it's also proportional to this. It also grows with the number of n's. And then one can sum the higher loops dilatation generators into a single dilatation operator. And then one can sum these coefficient into an interpolating function, which is a general function of lambda. So this f lambda, when lambda is small, it approaches lambda. But when lambda is large, it will be different. So this is effective coupling, as if one changes the one-loop to-Hopf coupling to an interpolating function. And this function is also a function of the CICJ, where CICJ are the weights of the corner box of the Young diagram, since this operator depends on the particular details of the Young diagram. Now we can see the anomaly dimension can also be expanded, and it will resum into an interpolating function. So the interesting thing is that apart from this interpolating function, there's a common factor, which is similar to the one-loop and two-loop anomalous dimension, which is proportional to Qij and Nij. And because Qij is the oscillator level and Nij is the number of open strings, so this part is protected by the oscillator algebra. So when comparing this function to the function appear in the one-loop expression, the lambda is effectively renormalized into an interpolating function, f lambda. So this, because this algebra is robust because it's related to U2 symmetry algebra of two d-branes on the gravity side. So they are robust under loop corrections, and they're robust under the strong coupling, because the strong coupling it goes to gravity due as the symmetry of the two d-branes. Now on the gravity side, one can see the dilatation operator acting on this field operator acts like a harmonic oscillator Hamiltonian, and one can see this coefficient combined into effective spring constant. Because on the gravity side, among the branes, there's open strings stretched between brane I and the brane J, and their strength, the spring constant is proportional to the interaction strength lambda, and also proportional to the number of open strings. So this combination is the effective spring constant. So the spectrum is the effective spring constant times an integer, Qij. And in the one loop level, it's proportional to to-Hopf coupling. And at the higher loops, as we derived in the previous discussion, it will renormalize into effective coupling. One can understand this as effective spring constant, which get renormalized due to the interaction of the system. But this part, Qij and Nij, is still not being changed. That means they are protected by the oscillator algebra. So now let me briefly also summarize the main conclusions of the oscillator algebra and its role in the integrability in this context. So the oscillator algebra itself is rather robust because it can be reached by the U2 algebra of the two d-branes at a strong coupling by Inoue-Wigner contraction. And there's evidences that when this oscillator algebra is present in the high loop, the dilatation generators can be diagonalized. There's two evidence. One is that the high loop dilatation operators are polynomials of the generator A3 in large n limit. So because of this, they will satisfy the same oscillator algebra, but with different eigenvalues. And another evidence is that there exists BPS states as the ground states of the system. And they are also correspond to the zero of the polynomial, because the polynomial will annihilate the BPS states. This is the second evidence. So the main influence of the oscillator algebra to the spectrum of the operators are also twofold. One fold is that it protects the Qij, Nij dependence, where Qij is the oscillator level and Nij is the number of open strings. The second influence is that it will leave open an interpolating function. It cannot determine the interpolating function by the oscillator algebra alone. So the interpolating function has to be determined by the details of the interactions of the system. So this is the function of the 't Hooft coupling and also depend on the weights of the corner box of the Young diagram. So the integrability, the evidence for this integrability is also independent of other two evidences by other authors, which they use double coset ansatz, which diagonalize the space of Young diagrams of the impurity matrix fields, or by using global symmetries. And also the oscillator algebra is robust due to its relation to the U2 algebra. And this is also robust on the loop corrections and also at the strong coupling. So these are my main conclusions in the study. Thank you.
Time for a couple of questions. So I had one. As someone who's interested in ADS for condensed matter, we often study other theories than Yang-Mills.
Yeah.
How much of the structure do you think is there in other theories than n equal to 4 Yang-Mills?
Oh, you mean other theories due to the condensed matter
That's right.
system?
I thought it
Right,
would be a
right.
somewhat different or simpler CFT and looked at its ADS dual.
Right, right. Because in other condensed matter system, usually people are more interested in the macroscopic parameter, order parameter, such like a scalar order parameter or current order parameter. So here, I focus more on the integrability of the more inclined to the microscopic details. And the operator has a very large conformal dimension. So which means they correspond to states on the gravity side that has a very large mass, large energy excited on the gravity side.
So I guess what I'm then asking, if I looked on the CFT side and I took something that was integrable but other than n equal to 4 Yang-Mills, maybe,
Right.
I guess I'm just wondering, as far as I understood, most of the discussion was for the case of n equal to 4 Yang-Mills.
Yeah, yeah.
So are there other theories where the same kind of integrability appears?
Oh yeah. There's a beta deformation by Lee Strasser, and also they have a gravity dual by Luding-Marissena, and they have a very similar structure. And in that case, there's calculations showing the similar mixing matrix, but the difference is that there's an extra phase factor. So here, in Luding-Marissena case, they have an e to the I beta and e to the minus I beta dressed from these two operators. So there's extra phase in the Luding-Marissena case. So in the Lee Strasser deformation, there's a similar expression, but with e to the I beta and e to the minus I beta added. So these are also integrable. There's also other theory. Usually occurs when supersymmetries are very large, because the supersymmetry in some degree also help to protect the property of the spectrum. That one example is by Nicholas Biset's SU22 centrally extended SU22 algebra. Because that algebra, centrally extended SU22 algebra, that algebra is so large such that it constrains the dispersion relation of the magnons as well as the 2-2 scattering matrix of the magnons by such algebra. So here, the reasoning here is very similar to the Biset's centrally extended SU22 algebra. So here, the oscillator algebra played a role, similar role as the centrally extended SU22 algebra. It will protect the spectrum to some extent by fixed partially the dependence. This part is fixed partially by the symmetry algebra. But this symmetry algebra is the algebra of the acting on the space of observables. It's not a symmetry of the fundamental fields on in the system, or it's not a symmetry of the Hamiltonian of the system.
Other questions?
Why did you refer always to the large N non-planar limit? I think of large N is usually associated with the planar limit.
Right. Yes. Right. So because the planar integrability in the usually is a large N limit, because in the planar integrability, if one consider 1/n corrections, and those corrections will not preserve integrability. So in order to preserve the planar integrability, the 1/n correction must be set to 0. And here it is, we have a 1/n correction added into the spectrum. The reason is that we have a planar contributions, say, of order 1, but we have a non-planar contribution of order 1/n squared. But number of diagrams is enhanced by number of n squared. So 1/n squared times n squared is comparable to order 1. And so because the number of non-planar diagrams is also very large when the number of fields are very large. Here, the number of fields in the operator grows with n in a parametric way, so it enhances the number of non-planar diagrams, such that the planar and non-planar diagram are of comparable size, and even they have an opposite sign. So their interplay become a discretized version of a harmonic oscillator Hamiltonian. So here, the non-planar diagrams are not neglected, but they are added, have a comparable size in the spectrum.
Okay. Other questions? No? Thank the speaker.
Great.
By Hongjun Wu from San Diego on quaternionic Landau levels and 3 junctions.
Good afternoon, everyone. First, let me thank the organizer, Professor Yao and Professor Zhang, for the kind invitation. It's really my great pleasure and honor to give a talk at this place. It's also my great pleasure to take the opportunity to introduce our work on generalizing the Landau level from 2 dimension to high dimension, mostly in 3 dimensions, since it's physically realistic. Yili, he was my former graduate student, and she's really outstanding as main driving force of this work. She's currently at the Princeton Center of Theoretical Sciences as a postdoc fellow there. Let me also thank my collaborators. First, Professor Shushen Zhang gave us a lot of help and encouragement. We can also see that this work, the research style is heavily influenced by his research style. Also, fruitful collaboration with high energy collaborator Ken Intrigator and Professor Yu at Chinese Academy of Sciences in Beijing, and also Dr. Xiangfa Zhou. He's my visiting scholar from University of Science and Technology, University of China. This is a series of work on this topic. Also, I thank many friends and colleagues for many lot of discussions and suggestions. In particular, I would like to thank Professor Hui Hirsch, and this work is grew up with intensive discussion and debating with him. This is the outline of this talk. First, I will briefly explain what is quaternions, and then we try to see how to using the quaternion analytic condition to build up Landau levels in both 3-dimension and 4-dimension, but mostly we will look at 3-dimension. So basically, we think that the analyticity condition is a useful rule to select the wave functions with good properties for, here is for non-trivial topology. In 2 dimensions, for the quantum Hall state, the lowest Landau level, we know that the wave function up to a Gaussian form factor, the polynomial part is a complex analytic function. But when we go to 3-dimensional, 4 dimensions, the Cauchy-Riemann condition is replaced by the quaternion analytic condition called filter condition. And physically, how to implement such a system, actually, conceptually, the Hamiltonian is quite easy, just the harmonic oscillator potential plus spin orbit coupling, but the interesting parameter region probably is quite difficult to realize in experiments. And this part is for the non-relativistic Schrödinger electrons. And we can also see generalized to take the square root of this problem, get the relativistic version of Dirac fermions. And we'll see that the Hamiltonian looks quite interesting. It's a complex version of quaternion structure. And there's an entire band of the zeroth Landau level with the 4 rotation symmetry. They are half-fermion zero modes. We don't know that whether it's corresponding to a field theory anomaly or what kind of anomaly is it. Now let's to the introduction. Actually, everyone of us agree with that the complex number is important. But actually, dated back to the 16th century, the first when people first discovered the complex number, the I, is not from the solving the equation of x squared with minus 1. Imagine if we live at that time, we could simply see that this equation has no solution. The real reason for people to accept the imaginary unit is because people want to solve this cubic equation. There's a famous Cardano formula. It turns out that suppose we start with a very simple cubic equation, all the coefficient is real. And we also know it has a 3 real root. But if you plug in this coefficient, we need to take a square root of this discriminant, which is minus 1. So start from real coefficient and end up with real root, but in the middle, we have no way to avoid the complex number. So this fact make people to accept the complex number. If we open our mind, then we will see a lot of, after a few hundred years, development, very beautiful result. For example, the Gauss gave a geometric interpretation of complex number, which can be very elegantly described 2-dimensional rotation, and physically corresponding to a fixed axis angular momentum. The Euler formula expresses complex number in terms of the U1 physics. It's widely used in optics, circuit, and quantum mechanics. And the real, big achievement is the development of the complex analysis. If we put the constraint of a complex valued function by the Cauchy-Riemann condition, and we know build up an entire field in the 19th century, since the 19th century, the complex analysis. And for example, the two-dimensional, for the quantum Hall effect, two-dimensional lowest Landau level wave function is satisfies this condition. And complex analysis, a lot of beautiful results. For example, the algebra fundamental theory, you can also even use to study the property of integer numbers, for example, the distribution of prime numbers, Riemann hypothesis. Come back to physics. For complex number, for in classical mechanics, when we describe wave equation, sound wave or electromagnetic wave, the complex number is a convenient but not essential. The really essential began to in the quantum mechanics. In the Schrödinger equation, actually, this I is very important. In fact, Schrödinger himself wanted to eliminate this I because he felt that it's unpleasant, but he didn't succeed. The next step is that since the complex number is quite convenient to describe rotations, but the real rotation in our world is three-dimensional. So Hamilton thinks that whether we can extend the complex number to describe three-dimensional rotations. He quickly found that if we want to extend, we need to extend another two imaginary units. So we will have a quartet of real numbers, we call it quaternions. And these quaternions also form a division algebra, which means that if A times B equals 0, then either A need to be 0 or B need to be 0. But this is not the ordinary division algebra because that they do not commute, because since the three-dimensional rotation, they do not commute. And this is the algebra figured out by Hamilton about 170 years ago. This is the extension of the Cauchy-Riemann condition called filter condition. And this is a counterpart of the Cauchy integral in the quaternion language. This is called the quaternion plaque, which shows that Hamilton discovered this multiplication table when he passed this bridge in Dublin about 170 years ago. But Hamilton was quite ambitious. He wanted to develop an entire field of quaternion analysis could be as powerful as a complex analysis, but he didn't succeed. He got a partial success. He indeed he was able to describe three-dimensional rotation and also four-dimensional rotations using quaternions. And this is what he did. Any rotation in three dimensions can be characterized by a rotation axis and a rotation angle. And rotation axis is characterized by a solid angle, and he mapped to a imaginary unit quaternions. And each rotation operation is mapped to a unit quaternion. This is the rotation angle and the rotation axis. And we can clearly say using today's language, this is nothing just like, if we map to Pauli matrices, it's just the SU2 rotation belong to the S3 sphere. Then how to do the rotation for any vector in the three dimension? It mapped to a purely imaginary quaternions. For example, let's choose a particular point for this along the unit vector along the z direction, then map to a quaternion imaginary unit of k. And if you want to do rotation, just put this k in the middle and sandwich it between this rotation. And if we take this rotation q, go through all this three-dimensional sphere, then we realize a mapping from S3 to S2. So three-dimensional rotation in terms of quaternions is naturally, it is a explicit representation of the first Hopf map. Okay. Next, let me try to use quaternions and try to extend the Landau level, go to three dimension, and mostly we'll talk about the three dimensions. Before we go to higher dimension, let's look at, review what we learned in quantum mechanics, what happens in the two-dimensional Landau levels. And this is the Hamiltonian P minus A square in the magnetic field, and this vector potential, we use the symmetric gauge. And this is the eigenequation of this is the second order differential equation. But if we are only interested in the lowest ground state, this equation can be factorized to a first order linear differential equation. And this is their creation, their annihilation operator of the harmonic oscillators. We are in 2 dimensions, so we have in the x direction and the y direction. So lowest Landau wave function is a 0 mode of this operator. And this is a wave function of 2 dimensions. We write a Gaussian form factor, and this is supposed to be a polynomial part. So in general, it should depend on both and z and z bar. But you ought to satisfy this condition. It shows that it's equivalent to say that this polynomial part is only depend on z. It means that it's complex analytical. And this is a complete basis for the analytical polynomial in the complex plane. The power of this polynomial, which physically means that the orbital angular momentum of such a system, we can see this angular momentum can only take positive values, not negative values, which means that the cyclotron motion of electrons, the direction is fixed by the magnetic field. The electron cannot rotate in the opposite direction. So you can see that the Landau level, although in the past decades, a lot of tremendous development of topological state and a lot of material in the semiconductor, most of them semiconducting material in the lattice, and the electron wave function are Bloch waves. And compared to Bloch waves, the Landau level wave functions, they are simple, explicit, and elegant. Basically, they are harmonic oscillator wave functions. But we don't need to want to use all these complex, we don't want to use all these harmonic oscillator wave functions. We only want to select part of them with good properties. So the 2-dimensional wave function, although they are complex valued, but depends on both x and y. So generally speaking, it's not an object of the complex analysis, but rather than real analysis. In order to select the part with good properties, we impose a Cauchy-Riemann condition, and which means that this wave function should have a complex analyticity. Using physical language, in physics we call it chiral. And the chiral is physically implemented by the magnetic field. And based on these results, it's greatly facilitated to construct even the many-body solution for the fractional quantum Hall state or Laplace wave function. And this is an analytical function of multiple complex variables. Now, if we want to go to a higher dimension, then we don't have a complex number anymore. There's pioneering work by Professor Zhang and Jiangping Hu beautifully extend the Landau level to the 4th dimension, putting in the background of SU2 gauge field on the compact space of S4 field, S4 sphere. This used a sophisticated mathematical concept, the second Hopf mapping. They construct both the integer and the fractional quantum Hall states. A very important point is that such a state maintains time reversal symmetry. And later on, Xiaoliang Qi and Hughes and Professor Zhang, they show that by dimensional reduction from this state can get also 3-dimensional and 2-dimensional topological insulated state. And now we want to come back to the flat real space. Say, let's come back to the 3 dimensions. What we need actually is quite simple. It's nothing beyond harmonic oscillators. But again, we don't want all the wave functions of harmonic oscillator. We need to do some selection. The selection criterion is quaternion analyticity. And the physical implement is spin-orbit coupling. So this cartoon basically shows the general configuration of the 3-dimensional Landau levels. As you can see that it's really like the configuration of of a top, as we learned in the rigid body mechanics when we learned the classical mechanics. So basically, you pick up, we choose a right-handed child with a 3 orthogonal axes, E1, E2, and E3. E1, E2 define a plane. And for any coordinate in the 3-dimensional space, we do a projection into this plane and make a complex number, and define a complex analytical functions in this plane. How to decide the chirality? We need the third axis, which is we need the spin along this axis, and spin direction is parallel to the chirality of the orbital motion. And then we can, once we have this, we can perform an arbitrary SU2 rotation, and we can exhaust all the possible configurations of the 3-dimensional Landau level state. And this is, we can do in the symmetric gauge. There's another version of this Landau level state in the Landau type gauge. Today, because their symmetry structure is not so beautiful, today we are not discuss it. Basically, let me use a few seconds to describe it. It's quite similar to yesterday Xiaoliang's talk using layer by layered construction. So basically, if the 3-dimension can cut many slices, each slice is a 2-dimensional plane. On this plane, the electron mode has fixed helicity mode. And different helicity modes are shifted along the different directions along the axis. Positive helicity moves along the positive direction of the axis. Negative helicity move along the negative direction of the helicities. And the advantage of Landau level is that during this process, the energy level remains flat without dispersion. And all these pictures can be easily generalized to even higher dimensions. But today I will focus on this symmetric type gauging. Now let's come back again, look at how to solve these Landau levels. Again, we look at the 2-dimension, for example. This is the Hamiltonian. Through the minimal substitution, we get the quantum mechanical Hamiltonian of electron in the magnetic field. In the symmetric gauge, let's expand this Hamiltonian. P square goes here, A square goes here, and A square becomes a harmonic potential. The crossing term is proportional to orbital angular momentum LZ, is the orbital Zeeman term. And this orbital Zeeman term commute with the harmonic potential. So they share the same set of eigenstate, so which means that the Landau levels are nothing but just a harmonic oscillator will function. So this is one of the reasons why we like the Landau level so much, because it's very easy to understandable for even for students with first year quantum mechanics class. Then, but 2-dimensional harmonic oscillator doesn't look like a very exciting system. Why it can give us non-trivial topology? The reason is that the organization is different. The left-hand side is an energy level diagram. We can find this in any quantum mechanics textbook. The horizontal axis is the magnetic angular momentum. This is the energy of the harmonic oscillator. So if we look at, for example, the ground state S level, so the next state is a pair of P level, and then is degenerate S level and D level, and so on. If you look at the spectrum in a horizontal way, then each level gets a finite degeneracy. You have positive chirality and negative chirality, and add together, it cancels. So nothing spectacular. But if we change our viewpoint, look at the same thing from diagonal way, then become Landau level. Why we can do this is because the Landau level Hamiltonian has an extra term, orbital Zeeman term. This term also gave us a linear dispersion of spectrum with respect to orbital angular momentum. The original harmonic oscillator spectrum gave this dispersion. This dispersion and this dispersion have opposite sign, they completely cancel. So when we add this orbital angular moment, the orbital Zeeman term is equivalent to I rotate this tower to be flat, so this became a lowest Landau level. We get infinite degeneracy with respect to angular momentum. And nicely for this state along this red line, you can see that is a complex analytical function multiplied by Gaussian form factor. Now, how to do it in 3 dimensions? Apparently, magnetic field doesn't work. No matter which direction you choose for the magnetic field, the electron motion parallel to the magnetic field does not fail Lorentz force. So we should replace the direction of magnetic field with a polymatrices. In other words, is a CO2 generalization. And in solid state, usually we call this a Aharonov-Kashel potential. And then this is the Hamiltonian, the P minus A. A takes this Aharonov-Kashel potential form, but we also need a scalar potential to maintain the spectrum to be flat. If we expand this term, we will get this part is a harmonic oscillator, but now it's a 3-dimensional harmonic oscillator. This part, the original is orbital Zeeman term, is replaced by a spin-orbital coupling. And the coefficient of the spin-orbital coupling here is very important that this is constant. So sigma dot L is a common term inside the atom for atomic Hamiltonian. But in the atom, the coefficient of spin-orbital coupling decays with a distance at 1 over cube. Here, we want it to be a constant. So, and such a Hamiltonian, you can see, has a 3D rotational symmetry and also has time reversal symmetry. Now, let me prove that the spectrum of this Hamiltonian is flat. Again, we can do it in a similar way in a 2-dimensional case. This is the energy level diagram of 3-dimensional harmonic oscillator. The lowest state is S state. Then the next highest state is the P level, and then it degenerates at S level and the D level. And all of them are 2L plus 1-fold degenerate. And more than that, you have a spin degeneracy up and down. But this is not a good eigenbasis. Because we want to use the spin orbital coupling, we need to consider the spin orbital coupled harmonic basis. So for each L, we can add 1/2 or subtract 1/2. And this is the reorganization of this spectrum. For S state, I have no choice but add 1/2. For P state, we can have either subtract 1/2 or add 1/2. So, and so on. Again, for this spectrum, if we look in the horizontal way, we get finite degeneracy and positive helicity and negative helicity, they cancels. But if you look at the spectrum along this red line in the diagonal way, we get lambda levels. Why we can do that is also because of the spin orbital coupling term. The sigma dot L has two different eigenvalues. Both of them are proportional to L, and we choose the positive sign or negative sign for the positive helicity sector or negative helicity sector. And here, for example, if we choose the sign here to be negative, it is the positive helicity sector, their spectrum become flat. For example, if we look at the lowest lambda level, they get degeneracy with all the helicity, all the state with a positive helicity, and their angular momentum take all the possible values. Actually, you can see that, here, it is the helicity replace the rho or chirality of the 2-dimensional case. Having proved the spectrum is flat, next we need to look at what the wave function looks like. The general speaking, wave function is quite complicated, but if we look at a particular state, which is the highest width state, the Jz equals J. In such a state, the orbital angular momentum and spin, they are parallel to each other, and both of them are conserved. Such a state, you can see the wave function particularly simple. Only spin up component is non-zero. Spin down is 0. And this spin up component only involves 2 coordinates. It's just the x plus iy. It comes back to a 2-dimensional case. But still, it is a 3-dimensional wave function. The Gaussian part is 3-dimensional. Then we can start from this highest width states, do arbitrary SU2 rotation, then we get a coherent state representation. And this is a coherent state where I briefly mentioned. You can choose any 2 orthogonal axes in 3 dimension, form a complex plane, and define a complex analytic function in this plane. And as I said, we need a spin structure, and the spin is perpendicular to this plane, and they form a trial for using the right hand. This picture can be generalized to arbitrary dimension. So basically for n dimensions, we can also pick up to orthogonal axis and define a complex plane. Using coordinate projection, this plane define complex analytic function, and we need a spin along, we need the spin locked with the orbital motion. So this is the, so Landau level, if we go to high dimension, naturally has a spin orbital coupled helical structure. Now let's look at comparison. From 1D to 3D. In one dimension, we do not get Landau level, but we do have harmonic oscillator levels. They are real polynomials. In 2 dimension, by the Cauchy-Riemann condition, we select a particular set of polynomials. They are complex, this, you can say the complex phase comes in a 2-dimensional plane. In the 3 dimensions, it means that this complex, this plane, originally in the 2-dimensional case, is fixed by geometry. Now this complex plane can rotate in the air. So as you can see, the configuration space essentially is a rigid body rotation configuration. So we know that it's a SU2 group space. So we know that SU2 is another language to SU2 is just quaternions. So this motivated us to think that there might be analytical property in terms of quaternions.
So if I fill the lowest Landau level, do I get a uniform density state?
No, it's not uniform. Only in 2D we have magnetic translation. In 3D, it actually is not uniform. Yeah. Now let's try to prove that there's a quaternion analytic version of niticity. And this is for the 2-dimensional Cauchy-Riemann condition that every one of us are familiar with. And this one extends to 3 dimensions called a filter condition. Filter condition, because quaternions do not commute, actually it has 2 different versions of filter condition. For our convenience, we just fix the convention that we multiply the imaginary unit from left-hand side. And this is the filter condition. If any function satisfies the filter condition, there's a Cauchy-Riemann filter integral. Now, this is our regular representation. Our wave function is a 2-component spinor, and each component is a complex number. Just like a complex number can be considered as a pair of real number, a quaternion can be considered a pair of complex number. Right? We follow this definition for the correspondence, multiply a j in front of the second component. And then almost all these ordinary transformation, time reversal, U1, SU2 rotation can be considered greatly simplified as multiplied by some quaternion phase. And our system that our wave function is quaternion valued. In 3 dimensions, it only depends on x, y, z. So the filter condition, we only need to keep the first 3 terms. We can also prove in 4 dimensions. In that case, we need the full filter condition, but now it's simplified. Our interesting observation is that the filter condition is rotational invariant. In other words, that if f is quaternion analytic, if you perform SU2 rotation, the new wave function is still satisfy the filter condition. And this we can this is simplify the proof. First of all, we can just choose the high east west state. Such a state is obviously quaternion analytic. All the coherent state can be obtained from a rotation based on this high east state. So all the coherent states also satisfy the quaternion analytic condition. Since the coherent state form an over-complete basis, so we prove that all the lowest Landau level state they can be mapped to a quaternion analytic function. And we can also prove the opposite, the completeness. Any quaternion analytic function corresponding to a lowest Landau level wave function in 3 dimensions. So basically, we can show that this is arbitrary quaternion analytic polynomial. It can be expanded in terms of a Landau level eigenbasis with a quaternion coefficient. Having talked about the Borg property, then such a system, if we put it for a open boundary with a spherical geometry, the edge mode also exhibits this helical surface mode. And this is a numerical calculation by diagram as a spectrum. You can see that for the angular momentum, which is small, then which means that these Landau levels, inside it does not touch the wall, so the spectrum remains flat. As the angular momentum increase larger and larger, then the Landau level touch the boundary, the energy is pushed up. So you can see that this energy level spectrum is pretty much the same as Professor Halperin did many years ago, but I should emphasize that here is that for each angular momentum J here, they have the degeneracy is much higher. Here, each of them is 2J plus 1-fold degenerate. And then we can also analytically derive the Hamiltonian of the surface spectrum. And so basically, each Landau level will contribute a helical forming surface if the boundary, the radius is sufficiently large. Locally, I can consider flat, and this the effective Hamiltonian is just like a helical Dirac Hamiltonian. Now, having discussed both the bulk property and the edge property, we can find an interesting correspondence. The left-hand side is basically the bulk property or lowest Landau level. In 2 dimensions, the polynomial part of wave function satisfies the Cauchy-Riemann condition. 3 dimensions and 4 dimensions, they satisfy the filter condition. If we look at carefully of this filter condition or Cauchy-Riemann condition, it looks very much similar to the Y equation. In particular, for the quaternion language, the IJK is just isomorphic to polymatrices. So, but this part is a Euclidean representation. If we move to the boundary, as you can see that in the 1D chiral edge mode, this is a one-dimensional Y equation, and now this just changes from Euclidean to Minkowski. So that's an interesting edge bulk correspondence from the analysis complex or quaternion analyticity point of view. How much time I have? Sorry.
Still about 15 minutes,
Oh.
including questions, maybe 10 minutes talk.
Okay, good. Now we have already explained the non-relativistic shorting electrons, and following an important rule I learned from my advisor, Professor Zhang, that whenever you find an interesting problem, don't stop it and take a square root of it. Now we will follow this instruction to take a square root of this problem, find the Dirac version, go to 3 dimension and 4 dimension, to find the relativistic version. And I should mention that this part is the main driving, the driving force is my student Yili. She designed this Hamiltonian by a beautiful analogy between complex numbers and the quaternion numbers. Again, let's look at the 2 dimension. This Dirac Hamiltonian put in the magnetic field, and we know that in solid state we have a real system of graphene. Again, this vector potential, I take this symmetric gauge by the minimal coupling. And if we use this harmonic oscillator creation annihilation operators, this Hamiltonian can be conveniently represented in this way. You can see the AX and AY, using complex number, make a combination between them. It can be easily proved that this Hamiltonian will square of it. It gives us the non-relativistic Hamiltonian of Landau levels in a supersymmetric pair. So the spectrum is just a square root of the non-relativistic version. We can take the positive square root and negative square root, so the spectrum is symmetric with respect to 0. And the 0 energy Landau level is particularly interesting. They are due to the chiral symmetry. Each level in this in this branch is a half-fermion mode. And its wave function is also very simple. It's only spin-up component is non-zero. And as you can see that, again, it comes back to the non-relativistic wave function with a complex analytic function here. Now, but how to do in 3 dimension or 4 dimension? My student observed that for the 2-dimensional case, you have a pair of harmonic oscillator operators. And here, the complex number, we have 1 and I. So we can make a linear combination between them. In order to exhibit the beauty of quaternions, let me directly go to 4 dimensions. If I want to 3 dimension, I can do dimension reduction, come back to 3 dimension later. So if you go to 4 dimensions, we have 4 axes, x, y, z, and the third axis I call is u. We have a quartet of annihilation operators. Certainly, complex number is not sufficient. We can make them combine with the quaternion unit. And we know that this is just isomorphic to these polymatrices. And then we can make a complex version because this A is annihilation operator. We know that in the semi-classic limit, it's just complex numbers corresponding to x plus IP. So this quaternion component now become complex numbers, so it's a complex quaternions. And then you make these complex quaternions, put it here, and make this complex conjugate. And this is the Landau level for 4-dimensional Dirac versions. And if we change back to the familiar representation using complex numbers, the dimension of the matrices changes from 2 by 2 here to 4 by 4. Okay. And now let's come back to 3 dimensions. That's easy. We just eliminate the first dimension. This is the Dirac Hamiltonian of Landau levels. And if we expand it, written the more familiar form, sigma dot p, the sigma dot p part is the ordinary Dirac equation. But now we have an extra term, the spatial dependent part. This spatial dependent part is a little bit, we were curious whether it's corresponding to a certain background gauge field. It turns out that it's not a gauge field. It does not corresponding to the minimal coupling, but rather a non-minimal coupling called polycoupling. It's basically here, if in this representation, is like an electric dipole moment coupled to a electric field. I should mention that a similar Hamiltonian was studied before us, and we didn't aware of this until we finished the paper. It's in the name of Dirac oscillator, but at that time, I think that its connection with Landau level physics and the topological properties was not noticed. This process can be generalized to arbitrary dimension. If you go even high dimensions, quaternions is not sufficient enough. But we know that quaternion is the same as polymatrices. Essentially, we need to use the high dimension version of polymatrices, Clifford algebra. And even dimension and odd dimension is slightly different because the SON and SO2N group, their spinor representation has a slightly different, but we can generalize to arbitrary dimension. But now let's come back to 3 dimension again and really solve this problem. Again, as I said before, this is a square root problem. So let me square this Dirac Hamiltonian. As you can see, it comes back to the 3-dimensional Landau level for Schrödinger electrons. But in a supersymmetric pair version, the difference is only the spin orbital coupling term, the sign is different helicity structure. And the eigenenergy is just a simple square root. And the eigenfunction can be easily constructed by solving these non-relativistic Landau levels like this. Again, the zero Landau level will function very special. Only spin up component is non-zero, spin down is 0. The spin up part comes back to the non-relativistic Landau levels, essentially the quaternion analytical polynomials. Okay. And then, again, very similar structure as the 2-dimensional case appear. In 2 dimension, we know that each of these zeros Landau level state, they are half-fermion mode in the sense of Jacob-Rabin mode. Whether the sign of the fermion charge is determined whether this state is a field or empty. In the 2D, and it can be shown that even in a vacuum, if you apply magnetic field, it will induce a non-zero charge with a positive half or minus half. And this is known as parity anomaly in the high energy theory. In the 3-dimensional case, this structure is almost the same. But the degeneracy is much higher because this zeroth Landau level, the degeneracy with respect to 3-dimensional angular momentum, not just the two-dimensional angular momentum. But we don't know how to call it, whether it call it anomaly. We know that in 3 dimensions there's no parity anomaly, so we don't know whether it's corresponding to a certain anomaly or not. If it is, what kind of anomaly it is. And again, we can solve this edgy problem. We choose a sphere. Inside the sphere is a 3-dimensional Landau level, and outside is a vacuum with a very large mass. And then again, this problem is square root problem of the old boundary problem of non-relativistic we saw before. So the spectrum should be a square root. For all the Landau levels other than the 0th Landau level, we can take the positive square root and negative square root. Okay. And for this 0th Landau level is special. The boundary spectrum, whether it's upper turn or down turn, is determined by the sign of the vacuum mass. For our convention, we choose the lowest Landau wave function only the upper component is non-zero, so it says the mass of this one. So if this mass is positive, we will go upper turn. Okay. So far, I have basically finished my talk. So basically, we show that the Landau level in a flat space can be easily extended to higher dimension. And the construction is very simple, just a harmonic oscillator, but we don't need all the state of harmonic oscillator. We want something with good properties. The selection rule is the analytic condition. In 3 dimension and 4 dimension, it's the quaternion analyticity. It goes to higher dimensions, essentially is the Clifford algebra analyticity. This problem can also take a square root to find the relativistic version. But so far, what we've done is within the single particle physics. It will be really interesting to see that if we add interactions, we hope that this quaternion version analyticity can help to build up a high dimension, for example, 3-dimensional Lofting state, and also whether there are possible experimental realizations. And another suggestion is that for people doing quantum mechanics instruction, I always want to persuade our colleagues to put this in qualified exam or final exams. And thank you very much for your attention. Yes.
Analyticity, I don't get it. Usually, I think of it in terms of power series, but quaternions don't commute. So you're doing it in terms of the analog of the Cauchy-Riemann equation? That formula is what gives you the analyticity?
The Cauchy-Riemann condition changes to.
Future integral. Or
Yeah, let me come to this.
So it's that integral that gives you the analyticity.
This is the analyticity condition. So F is a quaternion value.
So because the equation's elliptic, it's analytic, and you never have to deal with power series.
I'm not sure. Probably, as you said, quaternion does not commute. I'm not sure if you do this theory expansion, whether they are effective.
No, well, okay, so second question is, you have the Hopf map,
Yes.
and the Clifford algebras are built out of division algebras, so quaternions.
Yeah.
But if you want to go from S7 to S4, there's an octonian thing, there's special Clifford algebras.
Right.
And it seems like it's not just the Clifford algebra thing as you go up in dimension, but you need these homotopy group the sphere type things to happen. So in your conclusion thing, the first thing,
Yeah.
it seems like you need the S7 to S4 properties, which is more than just the Clifford algebra.
Right. We haven't considered that dimension, so I will stop at 3 and 4. For what you mentioned, octonions, Professor Zhang did good work before, according to the octonion structure in the 8th dimension quantum Hall effect, based on what the mathematical structure mentioned. But that's in a compact S7 space. What we did is in the flat space, in the Cartesian coordinates or Euclidean space.
Okay. Any other questions?
Yes?
Yeah, I think this is the version of the previous question.
Exactly. Yeah.
Or not constant linear
Yeah.
functions. So there, I'm just thinking, I mean, that's kind of a beautiful formula you have on the screen. So obviously something can be retrieved, but the fact that there isn't this theory of analytic functions of the quaternions must lead to some drawback.
I agree with you.
So
Yeah.
I mean, I appreciate your enthusiasm for quaternions, but there's sort of a reason that analog failed.
Yeah, that's basically non-abelian versus abelian. So indeed, as you said, if it depends on how you define analyticity. If according to your definition, then quaternion analyticity function is just a constant, then nothing beyond that. But if we relax this definition, as this, if we satisfy this condition, and then you can get this a counterpart of Cauchy integral in 4 dimensions. So it's not, in 2 dimensions, this Cauchy-Riemann condition corresponding to you take the derivative no matter what path you get consistent result. But you go to high dimension, this one does not mean that. It's not, not as strict.
Maybe I should ask this way. Can you tell us something about the set of f's for which that equation on the left is 0? What do you even call them?
F is a quaternion valued polynomial or function. It depends on 4 coordinates, x, y, z, and u, and take the derivative and follow this. So this is 0, then this is called Cauchy-Riemann filter condition.
Right, but if I ask you, what are the solutions to the ordinary Cauchy-Riemann equations, you say, well, there's a power series of z.
Right.
So now I'm asking, what are the solutions to
Oh.
the equation?
It's angular momentum, the spin orbital coupled angular momentum. It's just our solution. So basically, spin orbital coupled harmonics with a positive helicity means the L. Using physical language is like spin orbit coupled spherical harmonics. If you map it to a quaternion language, it satisfies this condition. So this condition, if we use this means that the angular momentum, right? The z to m's power is the orbital angular momentum eigenstate with a positive chirality, m larger than 0. And this one basically gives you the angular momentum in higher dimension, 3-dimension angular momentum, but with the spin orbital coupling. So the spin orbital coupled harmonics. The spin orbital coupled spherical harmonics, usually we write in complex spinors using complex number, but you can map it to a quaternion. Then it satisfies this condition. Or you can say this condition is nothing but a Euclidean version of the y equation. So any solution to the y equation, make it like a Euclidean one, also satisfies this condition. So we think that I think that still means something. Probably quaternion analyticity might not be the good language. This is y equation. So as long as something satisfies this Dirac equation or as a y equation, something is special. So we should select that.
Thank you. Great. If there are no further questions, let's thank the speaker.